Okay, let's get started. We're now talking about the thermochemical properties of materials. This is the area in which we consider how materials respond to thermal and chemical stimuli. They also respond to electromagnetic stimuli and mechanical stimuli, but we'll talk about that a little later. To understand how things respond to thermochemical stimuli, or in fact the stimuli in general, there are two things we have to consider. What the material or the system wants to do in response to whatever forces we put on it, and what it can do. The first part of that subject is thermodynamics. Thermodynamics is, in a sense, a description of the desire of material systems to evolve. It establishes what driving forces are available, what the material wants to do. However, the fact that a material wants to do something or a system wants to do something does not mean that it can. And that leads us to the second consideration, which is kinetics, which is what the system can do and how fast it can do that. So we'll begin studying thermodynamics, then kinetics, and finally we'll toss in environmental interactions to describe some of the special things that happen to materials. In thermodynamics, we get basically the conditions of equilibrium and stability. If we have a material in contact with its environment, with whatever forces are imposed on it, and if the material is in equilibrium under those forces, that means that it's not trying to change. It's happy. It's going to stay where it is. If the material is in a situation in which it deviates from equilibrium, then there is a driving force for change, and thermodynamics will tell us what that driving force is. In fact, we can go a little bit further, because there are also situations in which a material becomes so far away from equilibrium that it actually becomes unstable. If the material gets beyond the limits of stability, then it must change. Kind of a classic example of that was, let's take the diatomic molecule we talked about earlier. We talked about two molecules being bonded together, and if you pull them apart, there was a restoring force. You let them go completely relaxed, then they'll find an equilibrium position, an equilibrium separation. If you pull them apart a little bit, then there is a driving force trying to restore them to that original configuration, but the diatomic molecule is still in equilibrium under the forces you've imposed on it. It's not going to relax until you let those forces go. However, there is a maximum force that the bond between that molecule can sustain. If you keep pulling it apart and apart and apart, and you have a homework problem on this, you will finally get the force so big that the diatomic molecule can no longer keep itself together and it will spontaneously fly apart. That's the limit of stability that we're talking about. So we have equilibrium, we have deviations from equilibrium that give us driving forces from thermodynamics, and finally we have limits of stability beyond which a system must change spontaneously, and they actually do. We will, in thermodynamics, in studying equilibrium, find, first of all, conditions of internal equilibrium. That's that the temperature, the pressure, and the various chemical potentials are the same. The deviations from these conditions of internal equilibrium drive, for example, the diffusion of heat and the diffusion of mass. We also will find conditions of global equilibrium, in which the entire system will want to change, for example, to change its crystal structure or to change in some other global way. And the deviations from global equilibrium drives, for example, structural phase transformation. So we'll talk about those. What does the material want to solidify or melt or vaporize? Sure, it will diffuse, and well, assuming that the concentration gradient represents a chemical potential gradient, yes, it will diffuse out and become uniform. It depends. You don't confuse the thermodynamics and the kinetics. If there is a gradient in chemical potential, then there is a thermodynamic driving force to get rid of it. The simplest gradient in chemical potential is a simple concentration gradient in a uniform body. However, how fast that concentration gradient will be eliminated is a question in kinetics. It may be a very long time. As a specific example, you carry around a cell phone, presumably. In the cell phone, you have a whole bunch of transistors. Those transistors are chemically heterogeneous. They have regions that have one solute, regions that have another solute. That's how they work, as we'll describe later. That is an inherently non-equilibrium situation. You have got a concentration gradient in that device. If you didn't have concentration gradients, the device wouldn't work. Well, nature tries to get rid of those concentration gradients. And I can guarantee you that if you sit here long enough, that device is going to stop working. Because those concentration gradients are going to smooth themselves out. Hopefully you'll all be dead, or at least the device will all be useless before that happens. But eventually it will happen. So that's the difference between the thermodynamics, which is what the driving force is, and the kinetics, which is the response to that driving force. Can go even further. Over an infinite amount of time, that metal will flow like a liquid and drip down to the floor. We'll talk about that later. Okay. So let's talk about the thermodynamics. We have two laws in thermodynamics. The first just defines the internal energy. I'm going to go over this again because I'm sure you all forgot all about it during your 3-day vacation. Defines the internal energy, which is a conserved quantity. If a material gives up some energy, some other material or system must acquire it. We ordinarily separate the contribution to the energy into work and heat, kind of an artificial distinction. If you get further in thermodynamics, you'll discover that the work was done and the heat transferred, the sum of them gives a change in energy. The second law of thermodynamics is where all the interesting stuff is. The second law of thermodynamics defines something called entropy. The entropy of a system, as we discussed last time, is, if you want, just the measure of its evolutionary time. The entropy is how old the system is. And like time, the entropy of an isolated system can only increase. And any physical system you can imagine is an isolated system if you just include its environment with it, so it doesn't interact with anything else. The tendency of a system to evolve in its entropy, to evolve in time, is what provides the thermodynamic driving force. All thermodynamic driving forces ultimately come back to this. The system wants to evolve. It wants to evolve in such a way that its entropy increases, that is, it evolves into the future from the past. And that's what thermodynamics is all about. But even though it's not quite obvious, we can also associate entropy, the change in entropy, with the heat transferred in the change in energy. I'll talk about that today. We can also associate it with information. The less we know about a system, the higher its entropy is. And so that also is not, and I'll get back to that in just a moment. To describe entropy, we went back to a very simple system that is not that far off how you could arrange any system you wanted to arrange. You take your material or your system and you make it adiabatic. By making it adiabatic, that means you put it in some sort of insulated wall. You do something so that the only interaction it has with the rest of the universe is mechanical. The extreme case of an adiabatic system, you just isolate it, so it has no contact with the rest of the world at all. But let's let it have a mechanical contact. Now, there are two different ways that we can do mechanical work on a system. And the simplest one to visualize is just a gas in a container. We can do work on that gas in two ways. We can arrange a piston here, imagined to be frictionless, so that we do work on the gas by moving the piston. That work can be reversed because the gas can expand against the piston and push back on it. The second way of doing work is what we call reversible work, and that's with a paddle wheel or stirring rod. We can do work on the system by stirring it. but the system will never do work on us. That is, the system will not spontaneously turn this paddle wheel and do work on the universe. So we have these two different ways of doing work. One of them is reversible, the other is irreversible. No thermal interaction, this is an adiabatic system. Now what happens if we do these two different kinds of work on the system? Well, here we have to refer to experiment. And all experiments that have ever been done on all systems that can be represented in any elaboration of what I just gave you have the following result. If I do reversible work, for example, by moving this piston in and out, the states of the system can be described by energy and volume. Since I have a constant amount of material, there is no chemical variable here, it's fixed. The only variables I have, the volume can be varied by moving the piston, and the energy can be varied by doing work, either with the piston or with the paddle wheel. Suppose I do work with the piston. If I do work with the piston, then the states that I generate will follow a curve, something like this. The more I compress the system, the higher its energy is, and if I allow the gas to expand, the energy will come back down again. The system does work on the environment. So I generate a bunch of states along a curve, something like this. Now suppose that I do work with the paddle wheel. If I do work with the paddle wheel, that's isometric. The volume doesn't change, I'm just changing the energy. So the system moves up something like this. But I discovered an interesting thing. If I do a little bit of work with the paddle wheel and then let the piston move, I generate a set of states that's now along a new curve. This curve will never intersect that one. So when I do work with this paddle wheel, when I do irreversible work, I make an irreversible change. I move the system from one curve, one set of states that can evolve into one another, to another set of states that can evolve into one another. But once I have done that in this system, I cannot come back again. This is an irreversible process. So what does that tell me about time? It says that given this system, imagining all of the energies and volumes the system might have, I can divide those into the past, the present, and the future. The states that are right along the current curve that I can generate by moving the piston back and forth are in the present. I can go one direction, I can go the other. These are equivalent states. They have the same time if you want. The states that have lower energy at any given value of the volume, those states are in the past. I can't get to them. There's no way to get to them. I can't get to them by moving the piston. I can't get to them by turning the paddle wheel. If those states were ever occupied by the system, they were occupied at some prior time. So all of these states are in the past. These states up here are in the future. I can go to them by turning the paddle wheel at fixed volume, but if I do go to them, I can't come back again. So this curve that designates the states that I can now get to by reversible process separates the past from the future. If I look at the succession of such curves, each one of those curves I can assign a parameter to it. I can say, let me, for example, assign a reading of time. Since this state, this lower curve, must precede the second curve, must precede the third curve, let me call this time 1, time 2, and time 3. In fact, since I can add an arbitrarily small amount of energy by turning the paddle wheel, I can assign this time as a continuous variable that increases in this direction. For example, as I increase energy at a given value of the volume. I can call it the time, or I can do what people did back in the 19th century and call it the entropy instead. And they came at this in a very, very different way, but this is essentially where you ultimately come to. So this thing we call entropy is a measure of the evolutionary time of the system. If I define that time or that entropy properly, since these curves are arbitrarily close to one another, I can let it be a continuous variable that increases continuously as I raise the energy at constant volume, and I can put a number on it so that I can make entropy, I can put a unit on it if I want to. It makes sense not to, but people do put units on it. And I can then define it. If that's true, since every state of the system sits on some curve, I know it does because I can go to any volume and add an incrementally small amount of energy. Every state of the system sits on some curve. Every state of the system has a value of the entropy, just like it has a value of the energy in the volume. So I wind up with a situation in which these are curves of constant entropy. If I assign a numerical value of the entropy to each curve such that S is continuous, then I can write a function. Give me a state E and D, it's a point on this graph, and I can find out how to assign an entropy to them. So every state has an energy, a volume, and an entropy. The property of the entropy is that it can only increase. It can't go backwards, because I can move up in energy from one curve to another, but I can't come back down again. The other property of the entropy, of course, is it divides the past from future. The past includes all states that have lower entropy. The future includes all states that have higher entropy. And that's basically where the entropy comes from and how we can define it. Now, of course, I've described a very simple system, and you can say what happens when the system is more complicated. And if this were thermodynamics course, I could tell you we're going to move forward. I believe every system can be treated as I've described this system. It just becomes more complicated as the systems become more elaborate. Yeah. We'll get to that in a minute. Okay. Oh, there's some philosophical considerations on time. I'll pass over this. All right. I said that entropy could also be associated with heat. Now, that sounds kind of funny that time would be associated with heat. It can be. It's the following way. Suppose I have this function. The entropy is a function of energy and volume. If I just take its differential, ds is the partial of entropy with respect to energy at constant volume, dE, partial of entropy with respect to volume at constant energy, dV. You can show that, well, let me just say that the first thing that we can show is that the change of entropy with respect to energy at constant volume is a measure of the temperature. More specifically, it's a measure of the reciprocal temperature. Now, let me just assert that for the moment. I'll show it to you. I'll show it a little later. That the temperature I've defined in this way has the two properties that we associate with temperature. What are they? If we take two systems and we bring them into thermal equilibrium, they have the same temperature. That's how we measure temperature. We bring a thermometer in equilibrium with the system. If I take two systems and one has a higher temperature than the other, then heat will be spontaneously conducted from the high temperature system to the low temperature system. Now, what I will show you in just a minute, it's easier just to show it in terms of the conditions of equilibrium, that this derivative, partial of S with respect to the constant volume, of this function has the property of reciprocal temperature. Similarly, we'll find that ds dV at constant energy is the pressure divided by the temperature. So that I can replace this formal description up here with something that's a little closer to home. ds is 1 over T dE plus T over T dV. Now, how does I get to the heat? Well, suppose I just multiply through by the temperature. The temperature, incidentally, as I've written it here, is also a positive definite quantity. I know it's positive definite because I define the entropy so that the entropy increased as I went up in energy. Therefore, the change in entropy with respect to energy at constant volume has got to be a positive number because the entropy is increasing. So that says that the temperature is a positive number. So since it's a positive number, I can multiply through by temperature without changing the sign, move the E over to this side of the equation, and I get dE of TdS minus TdV. Well, the work that I do, the incremental work that I do in moving the piston in the process that I've described is equal to minus PdV, just from mechanics. So if dE is dQ plus dW, and dW is minus PdV if the work's done reversibly, then dQ is equal to TdS. So if I change the system in a reversible manner, add heat in a reversible manner, then the change in entropy is simply equal to the change in heat divided by the temperature. Turns out if I define things right, and this involves a little more mathematics I don't want to go into, you can show that I can measure the entropy in a way called the metrical entropy. This T is not just the temperature, it's the absolute temperature, temperature in degrees Kelvin if you want. And therefore I can actually measure the change in entropy, or measure the entropy, by going through processes, measure the heat added, measure the temperature, and integrate to find the entropy. So this entropy, which is time, is also intimately associated with the heat transfer, at least the reversible heat transfer. In fact, the work that's done, I didn't have a slide on this, let me just assert it. The work that's done can include both the reversible work PdV and then maybe some friction. If there's a bit of friction, then the work that's done is actually a little greater than PdV because it includes the friction. Turn that down here, and what you'll discover is that the change in entropy is greater than or equal to dQ over T. The entropy is the reversible entropy change dQ over T plus any further entropy change which is associated with friction. Irreversibility just throws time forward, gives you a bigger change in entropy than this would suggest. But the reversible entropy change is connected with the heat. So the entropy is time. The change in entropy is connected with the heat. I can't say the entropy is the heat because the entropy is a property of the state. You give me two states, I can tell you what the two entropys are. How the change in heat in going from one state to another depends on how I do it. So the entropy is a state property, Q is not. The entropy is, however, so the change in entropy is associated with reversible transfer in heat. The final thing I'll just kind of assert, if I have an isolated system, let's say, has a certain energy, certain volume, certain number of particles, I can crank and grind my solutions to Schrodinger equations, whatever, and I can calculate every possible state that system could be in. Every possible way to distribute the energy and the volume, if you want, over the particles it contains. If I let that be omega, the number of distinguishable states for a given value of the energy, distinguishable ways of arranging the atoms, distinguishable ways of distributing the energy and momentum among them, then I get a total number of independent states you can have. It turns out that a good measure of the entropy is just the logarithm of that number of states. And there's a Boltzmann's constant in here just because of the way it's usually written. This is just for dimensional purposes. But if I can just count all the ways, distinguishable ways that I can put the system together, that a third measure of the entropy is just a logarithm of that number of different ways. Now I said before, we calculate entropy from a knowledge of the system. The entropy, I can turn the sentence around. The entropy is kind of a measure of my lack of knowledge of the system. I mean, how many states can the system be in? Well, if I hypothetically knew, under the uncertainty principle this isn't possible, but let's go to classical mechanics, assume it is. If I hypothetically knew exactly where every atom in the system was and what its kinetic energy was, then there would only be one state that it could be in. I would know it was. Its entropy would be zero. The only way it can have an entropy is an uncertainty. I must not know what state it's in. It must be possible for it to be in a huge variety of states if it's going to have an entropy. And the more states it can be in, that is, the less I know about it, the higher its entropy is. And that's how this thing of entropy gets associated not just with degeneracy, but with information. The less I know, the higher the entropy of a system is. That gets tied into time in kind of an interesting way. Suppose you take a system like this. Now remember, I'll jump into just a tiny bit of quantum mechanics. You know in quantum mechanics we have an uncertainty principle. We can't simultaneously measure where something is or how fast it's going, which means we can't simultaneously measure its position and its momentum. There's an uncertainty. Let's suppose that at some time zero, I put a whole bunch of atoms in this box. And suppose that I configure them as precisely as I possibly can under the uncertainty principle. My lack of knowledge about them is the minimum that it would be under the uncertainty principle. Now I let them go. They start interacting with one another. Well, since I'm not quite certain what their positions and momentum were to start with, I'm even less certain of how they interact with each other. So over time, and you can calculate this out quantum mechanically, over time I'm going to be even less and less and less certain about exactly what state they're in. What does that mean? That means there are more and more states that they could be in, and therefore over time the entropy is going to increase. Now there is kind of a maximum increase under a fixed boundary condition, so that would find an entropy. But you see that as the system evolves, as I lose information, its entropy goes up. So all of these things, it's not so unreasonable that they're kind of all tied in together, and they are. A fundamental equation. Where you get to in thermodynamics is a fundamental equation. The fundamental equation is just a single equation that contains all of the thermodynamic information you have about the system. For a simple system, we have energy, volume, and there's also we have chemical content, composition. We can write the entropy, as we've already talked about S as a function of the NV. If we change the composition, that would also affect the entropy, so let me just throw those variables in. And the differential of entropy is 1 over TdE plus P over TdV, and then we have a, for convenience, minus chemical potential divided by temperature dN. This is a form of the fundamental equation. The fundamental equation tells me everything that I can possibly know or I know thermodynamically about a particular system. This is the form of the fundamental equation that pertains to an isolated system like I had back here. If I have an isolated system, what do I know about it? Well, really all I know about it, I can know its energy because I put energy in it before I sealed it off. I can know its volume because I fixed its boundaries. I can know what chemical content it has because I put all those atoms in before I sealed it off. So what I know about an isolated system are these variables, E, V, and N. I don't know the temperature of the isolated system a priori. I have no control over it. That's going to be whatever the molecules decide it's going to be. I don't know the pressure. I don't know the chemical potential. Those are the forces. But I can find them if I know the fundamental equation, if I know how the entropy changes with these variables by just differentiating. Partial of S with respect to E gives me the temperature. The partial derivative of S with respect to V gives me the pressure, P over T. The partial derivative of S with respect to the mole number of the K component holding energy, volume, and the other components constant gives me the chemical potential. So the quantities appear in the fundamental equation.